Welcome back. 322, lecture number 3. Before I begin, any question? You might have noticed on Friday I posted the homework, okay, for Friday, next Friday. Office hours should be on. I mean, at least for me, for sure, and from the TA as well. Whatever is specified on the syllabus. Now I forgot exact details. In case you have questions, we can also respond via email, okay, if you prefer that. And as you probably will notice, when I get a question via email, if it is appropriate, I share the whole thing with the whole class in case you have the same doubt. Okay, so question and answer. Okay. Anyway, with that said, let's continue with the first part of engineering economics. Showing this. Michael. Hopefully it's fine. Okay, so we are in the middle of discussing the economic equivalences. Okay, once again, it's a way to find equivalent amount of transactions which are placed in different point in time in a given cash flow. We have covered the P given F and F given P. Then we also did the P given A and also A given P, both they are just the same, just reverse. Today we are certainly covering the next, which are the so-called A given F and or F given A. And also at the end, we'll at least begin, if not finish, the theory about the so-called gradients, okay, which are the last part of the equivalence that we have covered. First thing first, the equivalence still involving, remember we discussed the uniform series, okay, cash flow, which is this one. Again, every arrow is supposed to be an A, where A is a given value, flat, okay, starting from whatever period for another given parametric number of periods n. So what we have already defined last week were the formula involving this equivalence, okay, the P given A, and A given P, which are really useful when you are dealing with mortgages or anything similar to that, okay, any kind of loan repayment schedule. Okay, you use this equivalence formula. Right now, we are just doing a step up. Well, before I do that, we also did the equivalent, the original equivalence, given an amount, let's call it P. We want to find the future amount, let's call it F. Okay, it was the first one we did. To conclude this overall equivalent between these three cash flow right here, we are left with identifying the equivalences between the uniform series composed of A's and a given future value identified with F. Okay. The first thing, actually, I would say the most confusing thing of this process, in addition to the formula themselves, which just look at the table and you pick the right amount of periods and the right interest to find the solution. What you need to be careful when you do this kind of equivalences is the following. Okay, given that this needs to hold for all three, okay, for all three the cash flows, as you may notice from here, the period at which your uniform series begins for your equivalence is, as we said last time, is one period after the period in which your P equivalent value is. Okay, are you following what I'm saying right here? There is one period in it. Okay, however, The other equivalence that you see from A to F, it doesn't have a symmetric meaning for that, because the period in which your equivalent F is placed is at the same period of your last A. So we are missing that kind of gap in between the end of the series and the actual F value. This is due to the fact that you want to have P and F also equivalent to each other, okay? And these are related by the P given F and F given A formula, which require F to be a period N, okay? So because of the choice of whoever came up with this modeling, you need to be careful that, as we will see in a minute also in the example, that when you are converting an equivalent series A to a given future value F, the period at which this future value will be placed is at the same period of your last A, is not one period after, okay? I'm just keep repeating the same thing because I know that it's gonna cause statistically error on you, okay? Anyway, just keep that in mind, and let's do a simple, very straightforward application of that. Okay, so you have an example right here. Also, let's identify the actual scenario, which makes more sense. Let's assume that you are very diligent and you are depositing $3,000. Let's assume that the period, actually it's already here. Let's assume the periods are years. So every year at the end of the year, you deposit $3,000 in your bank. Okay, starting from 1 year after the present, which usually is 0, and you do that for 10 years. Okay, at the end of 10 years after your deposits, you want to calculate how much it would be your total amount in the bank. Okay, the equivalent total amount in the bank. Okay, you can certainly do the calculation one by one. F given actually P. No, F given P plus F given P plus F given P. Okay, but that wouldn't be very efficient. You can use the F given A direct formula. Okay. So if you do that, you would directly apply the F given A equivalence calculation with the coefficient, which similarly than before is identified as such. We are, I didn't say that, but oh, here it is. We are given the interest rate associated with your bank account, 7% per year. It's, I don't know which country this is referred to, because 7% per year is extremely high now. You will never get anything like that, but let's assume that we are in a good period for that. So the assumed interest for your bank account is 7%. The number of periods in which you make your recurring deposit is 10, because you do that from 1 to 10. So the equivalent future amount, which once again, it will be calculated so that the number that you calculated is going to be at the same period of your last A. Okay, remember that. If you use this F given A calculation, this is where the resulting F will be placed. Well, I'll show you in a minute now. Actually, I'll show you immediately. How do you get the value of this F given A? You go in the back of the book. Here is nothing else than a scan of your back of the book. You go in the 7% interest page. You look at the F given A column, and you look at 10 period. So this is the factor that you will need to use to multiply your yearly contribution so that you are going to get how much you have in your bank account at the end of period 10, right? Okay, does it make sense to everyone? It should be pretty straightforward, I hope so. Once again, the only thing you need to be careful, a very typical error whenever I give anything like that, is that you do the right calculation, and I mean you, generic, you, the student, and you are placing the resulting value at 11. Okay, don't make that mistake. The resulting value, even though it doesn't make much sense, because intuitively you would see how much I have the next year, right, rather than how much I have right after I do my the last deposit. Okay, the amount is coinciding with the last period of your deposit. Now, what if, let me just give you an example what you could find in your quiz text. Okay, I give you something like that, and then I ask you, what if you leave this amount of money without making any other additional deposit? You're just sitting there. Okay, well, that should be a pretty straightforward calculation. You leave it there for 2 more years without any deposit, what you would have in the account at year 12. Okay, that is the question. What is your, let's call it F12 amount that you're going to be able to withdraw 2 years after you finish up with your deposit? Well, out here I call it F prime, so let's use the correct notation. Your F prime will be your F, so whatever you just calculated right now, $41,000 more or less, multiply by what? F even P 7% too, because I am finding the equivalent amount 2 years in the future, okay, applied to the original F just calculated before. If you do that, how do you get this blue circle value? You go again in the same page at the back of the book. In this case, you can easily also calculate it manually. The formula is pretty straightforward and easy. Okay, just one calculation. If you don't want to do that, just go in the 7% page. You look in the 2 periods actually row, and you get the correct factor, which is 1.144900. You make the calculation, and here is what will be your total amount in your bank after 12 years. Okay. Remember, assuming that we stop the deposits at year 10. Okay. All right. One thing that I know is notation gets confusing is that one question I get very often is say, why do you put F here? Well, F is only the notation used to identify this transaction. Okay? It's nothing else. It doesn't have to be called P. Okay, it can be called anything. Okay, however, you are applying a F even P factor to that value. Okay, that value you can call it whatever you want. Okay? So it's not an error. This F is just identifying this transaction that you want to calculate the future amount of. Okay. All right. Any question over this? Yes.
So would you have like F slash? First letter always your given. Second letter.
No, the first letter is what you want to find. So this means that I want to find a future amount given a present amount, an interest, and the number of periods.
Slash F.
Will be P given F. So P is what you're finding for. Okay. So again, this notation-wise gets confusing, as you can see. However, it is correct, even though it's confusing, because this F is referred to the future value of the original F. Okay. Of course, here the notation is kind of unfortunate, but kind of on purpose, so you understand what is the logic behind it. Okay, so you are pretty much calculating a future amount of this F value. Okay, whatever that F is represented. Okay, is it clear to everyone? Okay, all right. So these are tables we just discussed. Okay, now I like to show you this more complex example applied to actually a civil engineering project. I find this pretty informative and important, even though I don't find it extremely difficult, but certainly more complex than what we have done right now so far. So it also is put into context, okay, with a very simplified scenario. So it's taken from your book. a dam, okay, a very large civil engineering project is set to be built, okay? The initial cost of this dam is estimated to be $30 million, okay? Very high amount of money, obviously, but it's not uncommon for civil engineering project. And it's expected that it must be renovated every 50 years at an estimated cost of $10 million for every renovation. Okay, so this is the projected cash flow of the dam project. Okay? A very simplified projected cash flow of dam. And the associated cash flow diagram for it, as you can imagine, is like that. So you have an initial, and by the way, these are, I think is the books should have explained this better. These are all costs, okay? So you would expect the error to be down, okay? Because you are paying for your dam. However, in this particular example, you are asked a step beyond it, okay? In order to pay those costs, the question is, what should I set aside right now in a bank, okay? So at the interest of, what is it, 8%, so that I can withdraw from my bank whatever is needed to pay for my bank, okay? So this money, even though are arrow up, are assumed to be a withdrawal from your bank so that you can pay for your bank, okay? Does it make sense? It's like a step is missing here. So again, the question is exactly as I said, given that this is the necessary withdrawal to maintain and build and maintain our civil engineering project, what should I set aside right now? What should I collect from every investor right now so that we can put it in the bank and make sure that the dam is taken care of pretty much forever, okay? And actually, this example also highlight the infinite time horizon. Remember, I mentioned that last time. It doesn't really make sense, but it does make sense, okay? Because when you're dealing with a project like a dam, you don't really foresee an end of the project, okay? Eventually, something is going to happen, but you don't see it before, okay? It really should go in the builder's mind pretty much forever, okay? And so this is why the time horizon going to infinity, it does make sense also from a financial point of view, okay? So that's why we will use, as you can see, we'll see in a minute, the formula that we discussed last time, which involved a number of, infinite number of periods, okay? So anyway, this is the cash flow diagram of the bank, okay? In which you are supposed to make the initial deposit, which is supposed to be equivalent to all the transactions that you need in the future, okay? So what is the approach to doing that, okay? Since we are dealing an infinite amount of renovation period, is not straightforward, okay? So let's go through the thinking, how you solving this with the equivalence that we discussed so far. So if you focus any partial, you do in blue here. If you look at the cash flow, and if you focus in this portion of your cash flow, you see that it's repeated equally forever, okay? If you focus on any of these blue circle part of the original cash flow, you would have something like this, okay? Nothing is happening from 1 to 50. At the end of 50, you are required to withdraw $10 million. Okay, so you can say that this is your K plus 1, and is your K plus 50. where N is your 50. Okay, so with that said, you can transform equivalently this cash flow with the formula that we just discussed in the previous slides, with an equivalent cash flow which looks like a uniform series that is placed in every single period, every single year from 1 to 50. And there is a reason why we do that, and I show you in the next slide. Okay, first, let me cover this equivalence. So what do we have here? We have a future amount of $10 million, okay, which is equivalent to a uniform series of an unknown A amount, which is supposed to be withdrawn from your bank account every year from 1 to 50. And when I say 1 to 50, actually, it should be said, actually, it's in the next slide. So anyway, since I already mentioned, would be from K plus 1 to K plus 50, because it will be repeated exactly, okay, an infinite amount of time. And you need to do that calculation only once. Okay. So if you do that, your A, which is your unknown, this guy right here, is calculated with your F, and then A given F, IN, where I is 8% and N is 50. If you look at the back of the book table, we have that, yes, right here. You go into the 8% page. I know it's very small here. A little bigger, you look at the A given F column, you look at the 50 row, and you are focusing on this factor, which is what you need to use in the equivalence that I just showed. This one is your A given F, 8%. You do a simple math here, and you identify your A value equal to 17,430. So what we have found so far is that an amount withdrawn at year K plus 50 of $10 million, given the interest rate that we are guaranteed by the bank, is economically equivalent to a series of uniform transactions that goes from 1 to 50. Okay, are you guys with me so far? Yes.
Is that saying you'd have to withdraw the 17,430?
No, it doesn't say that you have to. It just say that it's equivalent to. It's the same for doing the financial calculation. So I'm not saying that I have to do this. I will go to the next step in a second. Well, the only thing I'm saying is that that is equivalent to doing that. Does it make sense to everyone? Okay, you will actually withdraw the $10 million when you need it. Okay, not the 7. Yes. I will get it in a minute. Okay, it's the calculation for P. Okay, so follow this first step first. Okay, I want you to understand this. Now we get into the second step. Okay. Okay, what I want to make sure that you understand that this is equivalent to this. So withdrawing this, it would be equivalent of withdrawing that. Okay, why are we doing that? I will tell you in a minute why. First, let me repeat that the same process can be done for any portion of the cash flow the same exact way, because K can be anything. It doesn't have to be only the first part of your cash flow. So if you do the same exact thing for every other section of the cash flow, you would get the same exact A. Okay, so pretty much you are telling yourself, I did it once and it will be absolutely valid for all the cash flow from now to the infinity horizon. Bottom line, we get to the point. If you do that, the original cash flow, this one, can be equivalently represented as such, where you have the initial withdrawal $30 million that it didn't change, and then as opposed to having $10 million every 50 years, you could have 17,430 withdrawn every year. And this would be exactly equivalent to the original cash flow. Now, once again, why are we doing that? Because our ultimate goal is to identify how much money I need to put in the bank now to make sure that that is available to us. Okay? And this is done in one single step only if you have this type of cash flow. Because if you had the original cash flow with the $10 million every 50 years, you couldn't directly find the fee. Okay, because we don't have the mathematical means for doing that. Instead, this step allows us to get to this one. Once we get to this format of the cash flow, you can do what? You have the P, which is equal to the $30 million, which doesn't need any transformation because it's already at the same period. Okay, we pretty much can ignore that. And we don't need any kind of bank transaction for that. But the remainder would be equal to your A series, this is your A, multiplied by the P given A factor calculated for an infinite number of periods, which we did last week. Okay, and if you remember, if you look at the slides from last week, it would be 1 over your interest I. So it's very easy to calculate that. So the factor that you need to use to calculate eventually your value P is 1 over I, so 1 over 8%, which is 12.5. This one is going to give us the $30 million, 217,875 total amount of money that you need to collect and put in your bank right now to make sure that you are able to pay for all the needed maintenance. And of course, the construction as well. So pretty much the $30 million goes away immediately because you pay at construction. The interesting part of this amount of money is the 217,875, okay, which is actually enough to pay for all the future $10 million every 50 years. It's very counterintuitive, but it is actually like that because the interest given by the bank is pretty high, so that in 50 years actually grows a lot, and then you can keep doing that forever. I show you a counterproof right now. Do you have any other question over this? Maybe you have some more questions after we do the counter, okay? Because the typical comment is, I cannot believe that $217,000 right now would be enough to do all that in the future. It seems like a very disproportionate amount of money, right? However, if you do the math, the pretty easy math, you can verify that, okay? So again, this is the total amount of money, the capital invested for your project. $30 million are immediately taken away, so you don't even consider them. You are left with 217,000 more or less dollar in the bank. Let's see what's going to happen to this that you don't touch until your 50-year first withdrawal. Okay, well, this amount of money in 50 years will grow so much using the F given P formula, which is 1 plus I to the power of n, remember that. And if you just do the math, you can try yourself, this $217,000 after 50 years will become $10 million, 218, more or less 217 again. Okay, there is a little bit of rounding here, okay, 218 is just very close to the initial amount. Then what happened after 50 years? So what I did is 217K, let's abbreviate that. Now, in 0, at year 50, will be equivalent at 8% to $10 million. 217K. Okay, we just proved that with a pretty easy financial calculation, didn't we? Okay, so after 50 years, what do we need to do? We need to withdraw $10 million to pay for the first maintenance. We do that, and what we are left with? We are left with $217,000 again, right? And this $217,000 will stay again in your bank account for another 50 years, which again will grow to get 10,217 again. And you repeat the withdrawal of $10 million, you repeat it again and again and again, forever. Okay, does it make sense to all of you? Yes.
Can you explain the 12.5 again? What is that?
12.5 is simply the factor, the P given A factor. See if I have it here. Actually, I have it. I forgot to show you. Right here. If you go into the 8% page, you look at the infinite row at the bottom, and you look at the P given A, that's what we use right now. It is 12.5, okay, which is really nothing else than 1 over I. Okay, so this is the P given A. Now I don't have the slides I showed you last time. If you look back at the lecture 2, the P given A given P, at the bottom, you have the case with n equal to infinity. Okay, so that's exactly what we are using. Yes?
So 1 over I.
No. It is not a coincidence. It's the actual formula. You use always 1 over I for the P given A when n is equal to infinity. Of course, it's going to change because I is 8% here. It depends on which interest you have. Okay, does it make sense to all of you? I guess the thing that you need to get over, because it's not intuitive, is how much is the power of the interest accrual, right? Because it's difficult to see that leaving this relatively small amount is in 50 years is good enough to grow to 10 million and plus, but actually it does. And feel free to verify. Of course, it's really helped by the fact that we have an 8% interest, which is really high. Okay? You don't really get that. But actually, with the projects, negotiation, when you do project building, the banks that is dealing with the project, actually, these are the type of interest you get. It's completely different than what you get in a bank account, okay? Because we are talking so much money, right? So that you always negotiate higher interest rate. Okay, so it's not out of the world having it. Okay. Let's see. So I think this is a pretty informative example, okay? Also very well applied to a civil engineering project. I did these steps for the purpose of making you understand how to play with these equivalences, that you will be tested on it for sure in the first quiz, okay? In particular in the first, okay? As we will see later, okay, another way to solve this, we will see that in a second part, but I'm giving you an anticipation. Rather than doing this conversion that we did here, using the F given A, you can directly calculate P by having this uniform series of 10 million every 50 years. But in order to do that, what you need to do, you need to calculate the interest over 50 years, because the period, instead of being 1 year, it becomes 50 years. Okay, so what is the equivalent? We have here the interest over one single period, but what would be the combined interest for the whole 50 years? Okay, if you have that value, then this is simply going to be a P given A with an infinite amount. What we don't have is the interest associated with that 50. Okay, but we do this calculation later when we are able to convert interest for different periods. The same interest for different periods. Okay, but anyway, for now, I want you to be able to recognize this modeling and be able to. Okay, save this for us. Okay, now I'd rather go and explain at least one of the gradients And next time I will do probably more examples, okay? So I still have 15 minutes. So if you look at the back of the book here, we are pretty much covered up to this point, okay? Now, we have this gradient, which is also covered by the book, and we are looking at that right now. And we have also an additional gradient that I talked either later today or next time, which cannot be put in the table because it has an additional parameters that you would need a three-dimensional table for that, which is obviously not very practical. But anyway, let's start with the easy one, okay? Which is what is called the arithmetic gradient series, okay? So let me go into the definition of that. What is that arithmetic or linear gradient calculation? It's again an equivalence, okay? An equivalence between a given amount P, okay, and a so-called linear gradient, which is identified with just the number G, but graphically it looks like that. Okay, so this one is the meaning, and it's also in your book. The meaning is that, well, how much I need to put in my bank right now so that I will be able to withdraw this linearly increasing amount of money in the future, starting from a zero amount of money 1 period after my deposit. Okay, this is how they set up the model. Okay? I don't really know the reason. It's probably some simplicity reason. Okay, well, what you need to remember is that the gradient starts with zero, 1 period after your equivalent amount. So the confusion starts by the fact that it looks like we have 2 period gap in between the equivalents, but it is solved by the fact that the first value is a 0 one for the gradient. Okay, so the gradient starts with 0, goes up linearly like that. Okay, of course, for a parametric number of years, or periods, from 1 to whatever n. Okay, n is a specified parameter. Again, I won't test you on the math, but for the math enthusiast, how do you go to the final result? You can consider every single one of these arrows as a future value that you can convert to the present by a simple given f. Okay, you do that for every g in your chart. And if you do that, you do some mathematical manipulation here. If you call x this amount, you can put the x into your original formula, and then you recognize that this part in parentheses is a known mathematical series, which can be written also in this format, okay, in a more compact form. Now, this is allowing us up to here. So this is allowing us to finally get to the final formula, which is represented right here. You can certainly put this in your calculator if you want to go from P to G or vice versa. However, you are welcome to just use the back of the book tables, okay, in which you have, again, all the values that you need calculated from pretty much any case. Okay, so I think the best strategy is to show you an example over that, and I do the other gradient next time. Okay, so any question on the modeling, on the theory? Okay, again, the only thing that you need to be careful about is this hidden arrow, which is 0, which gives you the impression that there is a gap of 2 for the equivalence, but it's actually not. So the next example is actually pretty straightforward, but it makes the point. It makes the point pretty well. So taken from another source, whatever the description has, you can read it up, but eventually the important thing is that we are dealing with a cash flow like that, okay, which has this amount of withdrawals needed, okay, starting from 1,000 and 1,250, 1,500, and 1,750, and 2,000. And we want to see how much we are supposed to put in our bank right now in order to make sure that we are able to withdraw this amount in the future. So pretty much the same question as before, okay, with a different type of cash flow. Okay, so this, as you can see, let me tell you, you can always, if you want, do the silly way of calculating this. You can do a P given F plus P given F plus P given F. You can do that as well. Okay, certainly you can do that and you will get to the same result. However, the shape of this cash flow really suggests that you might want to use the gradient, okay? Because if you look closely, these amounts are starting from 1,000, however, then they go up to 50 regularly, okay? So you can kind of see that if you decompose this cash flow with a straight line like that, you would have here it is. Instead of this will be equivalent of having a uniform series straight $1,000 cash flow summed up to a gradient series. We start from 0 here and then goes up to 50. Can you guys see that? That should be pretty straightforward. If you superimpose these two cash flow, you would go and get the initial cash flow that we had, right? So, but this decomposition allows us to apply directly the formula that we just learned, okay? The first one being what we already know, the P given A calculation, okay? So you can say that your original P is P1 plus P2. Okay? So P1 is, here is a little bit small. Calculation. So P1 is your A, where A, the book calls it A1, so whatever, A1 equal to your $1,000, which is this guy right here. Okay, and then simply converted into an equivalent p-value with the P given A formula. Okay, this is nothing new, we have done that already. But then you also include the gradient calculation, because this part, the second portion of your initial investment, is equivalent to the gradient which starts from 1 with 0 and goes up to n equal to 5 with 1,000. So it goes up of the quantity of 250, G equal 250 in every step. And this is summarized by the G. G is your 250. 250. Sorry about that. And then you apply the P given G 12% 5. Now, where do you get this P given G 12% 5? You go into the back of the book, 12% page, here it is. 12% page, you go into your P given G formula. We have number of period is 5, so the P given G 12% 5 is right here, 6.397. Okay, so this factor is nothing else than the result of plugging in the parameter in this formula. Okay, that's nothing else than that. Okay, but I use the table to make it easier. So this 6.397 is right here, and you multiply your G value by that. So the second contribution, even though it's not explicitly shown here, is added to your P given A formula or before, and you eventually are able to get the 5,000 more or less, 5,200. Total amount of money that you need to put right here in order to make sure that you are gonna have this amount available for withdrawals in the future. Okay, good enough. Any question over the example? Or anything else? Yes. The gradient is always defined, the model requires that the gradient start with 0. Not exactly period 1. In period 1 here, yes, but in general, 1 period after your equivalent P. So, since you asked, you can have P at period 11, let's make it more generic, okay? And then your gradient will start at 0 right here, and then G at period, this is 12, so this is period 13, and then 2G at 14 and so forth. So 0 is 1 period after your P, which in our example, it was 1. Okay? Any other question? But yeah, sorry to keep you, to build on that, you just remind me, one very common error when I grade this, okay? Sorry, it takes only 30 seconds. If you have a gradient like this, okay, G, 2G, and so forth, 3G, and so forth, okay? This is period 4, 5, and 6, so that your 0 is at 3. Okay, and I ask you, what is the equivalent P at 0? Okay, you're gonna be careful here, because if you apply the P given G formula, you are gonna get a value which will be placed here at period 2, 1 period before your 0. Okay, so in order to get the value that I asked even 2 years in the past, you need to do an additional transformation, okay, which will be a P given F. Does it make sense? Instead, if you directly do the P given G at this value to calculate that, you don't get the right answer because it doesn't have the right model. Does it make sense? So it needs to be consistent with the model, okay? So if there is another gap in the middle, you need to do a double transformation. Okay? Whatever is appropriate for it. Thanks for the question. I hope I further clarified it. I'll see you on Wednesday.
I think I peek at these numbers real quick.
Sure. Thank you. Yeah, I didn't post it, but I will post it.
Yes, I did the homework.
Okay.
I did 2 through 4 pretty easily with the first one. Some of the things. So.
Right now, okay, if it's quick, yes, otherwise